Today we're looking at derivatives of inverse functions. So an inverse function is a function that swaps x and y. So from pre-calculus, this little diagram, we drew something like this last year. If you have y equals f of x in red as your original function, then its inverse would be reflected over the line y equals x, which is this green dashed line, and its inverse is g of x. So in this section, a lot of the problems will use g of x in place of f inverse of x. So just know that those are the same thing. I always will rewrite them as f inverse of x because it's confusing otherwise to me. So that's a really quick reminder of what inverse functions are. And as you can see, the red line and the blue line, I did my best to draw these reflected over that line. So if on the red line I have this coordinate at 2, 3, then on the blue line it should be at 3, 2. And you can see that those reflect over y equals x. So that's what's causing the reflection, is just the swapping of x and y. For the derivative of an inverse function, if you look at these 2 points I highlighted right here and here, you can see that the orange dashed line represents the tangent line at those points. And what is different and what's the same about these is that, so the slope is still positive, but what it is the reciprocal slope. So if we say that, it's hard to tell exactly what this slope for the red function is, but let's say it's, looks like roughly 2, positive 2. Well, this slope is going to be the reciprocal of that, which is 1 over 2. So, and you can kind of see that it's roughly 1 over 2. So the slopes are just reciprocal. So this isn't really a complicated visual or anything like that. So all it is that your slopes are going to be reciprocal for the inverse derivative. So let's look at that formula. Keep that on both. Keep both those on. So the derivative of an inverse, f inverse prime of x, is simply going to be 1 over f prime of the inverse. And what I'm going to do is do multiple examples for this, no two being the same, because that's generally how inverse questions are. So I'll start out with our first one, which is here. So a function and its inverse have symmetry about the line y equals x. What is the slope of the inverse of the function? Well, this is a linear function, so this question I'm not going to make too complicated. So if I rewrite that just as y equals 1/2 x, what's the slope? Well, the slope of that is 1/2. So the inverse it would just be 2. So it's going to be the reciprocal of that. So the inverse, the slope of the inverse of the function is just 2, because it's the reciprocal of 1/2. So for linear functions, you don't have to go through the whole formula or anything like that. It's just that simple. Okay, so let's make it a little more complicated. So I do have that formula right below so that we can reference it. So it says calculate g prime of x, where g of x is the inverse of f of x on the domain x is greater than or equal to 0. Okay, so we don't really need the domain there. I just have to state a domain in order for it to work. So we're going to use this formula in this case. So let's find the inverse first. So this is just review from pre-calculus. X to the 4th plus 10 is our function. We swap f of x with y. And then we can swap y and x. And then we solve for y. So x minus 10 equals y to the 4th. And then you take the 4th root. Okay, so f inverse of x is y. It's going to be the 4th root of x minus 10. Okay, so now we have one part of our derivative of the inverse formula. Okay. So then all we have to do is plug in the inverse into the derivative of our original function. So f prime of x is 4x to the third. Okay, so what we're going to do is plug our inverse into our derivative. So if I just sum this all up, f inverse prime of x equals 1 over f prime of the inverse. Let's plug the inverse into the derivative. So this would be the fourth root of x minus 10 plugged into 4x cubed. Just like that. So that is the derivative. Next example has one of these tables. So if f inverse is the inverse function of f, what is the value of f inverse prime of x? Okay, so for this one, what we have to do is take into consideration that the inverse swaps x and y. So if you plug in, let's say for example, I'm going to do this, this is not part of this problem, but if you have f of 3 equals 5, for instance, then f inverse of 5 equals 3. So the inputs and outputs are going to switch when you're using, between the inverse and the original function. So this says f inverse, what is the value of f inverse prime of 6? Okay, well, that's basically taking the derivative at 6. So our function that we need okay, so we're going to use that. So what do we do? Well, what is f inverse of 6? Because what we're trying to find is f inverse prime of 6. Okay, well, f inverse of 6. So on our table, we can see that 6 is here. So that's the output of the function. So it would be the input of the inverse. So if we were to plug in a 6, we would get back a 3. So now we're just looking at f prime of 3. Okay, now we take f prime of 3 given on the chart, and it's negative 7. So this would be 1 over negative 7. Okay, in this example, calculate g prime of 1, where g of x is the inverse of f of x equals x plus e to the x. So this is an example where I would actually change these g's to f's. So I'm going to erase those and replace them with f notation, and that's because it makes more sense to me. It's easier to follow. So f inverse is the inverse, and then we're looking for f inverse of x prime, which is, now it matches this formula. Now there's less confusion there. Okay, some functions you can't actually solve for the inverse first. So this one was asking for, actually made a little mistake there, just that. So it's asking for f inverse of 1. So since we can't solve this function x plus e to the x for its inverse first, because that e to the x is making it so we can't do that, what we have to do is find out just the specific value, what is f inverse of 1? And remember that if it's an input of the inverse, it's an output of the function. So what I'll do is take 1 and set that equal to x plus e to the x. And this problem, rather than trying to solve this, I'm going to solve this by inspection. So I just look at it. What number can I plug in where I will get 1? And the only number we can plug in is 0. So 1 equals 0 plus e to the 0. E to the 0 is 1, so that equals 1. So this tells me that x equals 0. So now we know the value. F inverse of 1 is 0. So now what we have to do is take the derivative. So I'm going to say f prime of x equals 1 plus e to the x. And now we have most of what we need. So if I go ahead and go into the solving stage, keep putting an x there, it should be 1. So we need f inverse of 1 prime, and then we just plug everything in. So f prime is 1 plus e to the x, and f inverse of x, or f inverse of 1, was 0. So this is e to the 0. And then we just calculate, and that gives us a value of 1/2. So that question is one of those ones where you have to use a lot of reasoning in every step, but ultimately it's pretty simple. Okay, in this example, f of x equals 2x plus 3. It's again one of those problems, since it's linear, we really don't even have to use the formula or anything. I already know the answer is 1/2. But what I will do is just show you in this example, solve for the inverse and then take the derivative of it. Because you don't always need that formula. So if we go y equals 2x plus 3, and y minus 3 equals 2x, divide everything by 2, then we would have your new function is going to be y equals x over 2 minus 3/2. So all I did was swap x and y, as well as move everything to the right. Okay, well, that's y, that's the function. And so this is the inverse function. So let's go ahead and change this to an inverse function. And again, this is all really not incredibly necessary, but may as well show you it. So f inverse prime of x, so if we take the derivative of that, we just get 1/2. So like I said, you could see that because with a linear function, you can see the slope. So you know the inverse slope is just going to be the reciprocal, but that's an example of where you can, solve for it and see it. Okay, so the last topic here, we're going to do just 2 examples. Inverse trig derivatives. So there are 6 inverse trig derivatives because there are 6 trig functions. I just have these 3 here because we're only going to use, we'll actually only use 2 of these. The ones that you need to commit to memory are sine, cosine, and tangent. So those inverse trig derivatives are ones that you'll need. Sine and cosine are pretty easy because cosine only differs by a negative sign out front. Okay, so in this first example, I deliberately used arcsine, and just know that arcsine, arctangent, arccosine, those just mean inverse. So that's the same thing as saying inverse, just another way to write it. So let's take the derivative. So f prime of arcsine of x squared. Arcsine is this whole thing is a chain rule problem because we have x squared plugged into arcsine. So I take the derivative of the outer function. So I'm going to use my sine inverse formula here. So this is going to be 1 over the square root of 1 minus, and whatever is plugged in here, we have to plug it in. So this would be x squared squared. Then multiply by the derivative of the interior function, which is 2x. So this would just be 2x over the square root of 1 minus x to the fourth. So that's our inverse derivative. Now we just plug in this 1/2. And so we'd get 2 times 1/2 divided by the square root of 1 minus 1/2 to the fourth. And you know, there's more simplification in here than right there you're done as far as the AP test goes, because there's nothing, you don't have to simplify. So this is just really 1, that would be 16, this would be 15 over 16. And then if I go through with that, so I'd have 1 over root 15 over 4. So 4 over root 15. And if I rationalize, I would get 4 root 15 over 15. So if I back up here, I just want to make you aware, just make sure I'm actually clarifying this. This is the derivative. And in this step, you have plugged in and evaluated. So beyond that, it's just simplification. So I just like to really focus on the idea that the problem is relatively short. It's just all a simplification that makes it more difficult at the end. So in our last example, we're going to take the derivative of inverse cosecant of e to the x plus 1. So you actually rarely see these types of problems, but I thought we'd do one that has more to it. Okay, so we do have a chain rule problem. So I'm going to take the derivative of the outer function, which is my cosecant inverse, leaving the inside alone, e to the x plus 1. So this would be -1, and wherever there's an x, I replace it with e to the x plus 1, the absolute value of that, times the square root of e to the x plus 1 squared minus 1. Now I multiply by the derivative of the interior function. So e to the x plus 1, the derivative is just e to the x. And so this unsimplified monstrosity is e to the x, or a negative e to the x divided by e to the x plus 1, absolute value of that, times the square root of e to the x plus 1 squared minus 1. And with something like that, I wouldn't even bother simplifying it, because that's one where the simplification, I did simplify it. It doesn't actually look more simple than what we have right now, so I would just say leave that alone.